So now is the talk about hacking and computer science brought to you by Sergey. A warm applause for Sergey.
Thank you. I don't really have any slack in time, so I would ask for questions after the talk. It's supposed to be an hour-long talk in my mind. Let's see how good I am at compression. So here is where I'm from. Dartmouth College, that little green blob on the map is New Hampshire, and the college has been founded. It's one of the oldest colleges in the US, 1769, and we actually have a hacker lab. I usually show this picture for, look at how much snow we have. But, in Berlin at this time, you're like, yeah, and then what? At least we can imagine that this is a pirate ship and has a suitable banner. What is this about? I'm not going to talk about any 0 days. I'm going to talk about an intensely personal realization, quest, revelation. And in the process of which I'm actually going to define hacking, which is entirely presumptuous to the point of being totally weird and ridiculous. Nevertheless, so feel free to ridicule. Nevertheless, at some point in my life, I realized that what I have so much fun with actually is very, very deep fundamental computer science. And in fact, I've learned more about the nature of computers and programming and computer science from hackers than from graduate school. And basically, these kinds of citations, which you put in a LaTeX paper, are probably the most illuminating. And of course, the problem is that sometimes you have to quote posts on BugTrack. We'll come back to that post. It's quite an interesting one. So my answer is that hacking is actually a unique and distinct engineering or research discipline that has simply not been formally recognized as such or defined as such. And when I talk to academic colleagues, their eyes go wide and they ask what I've been smoking. But I'm going to stand on that, and I'm going to give an introductory philosophical argument, after which we're going to jump back into a lot more technical stuff. But first of all, of course, you need to define what you're talking about. Secondly, anything worth the name of a discipline, of a significant human technological or scientific pursuit, must be hard. Not only it must be hard, it also has to address something that is really, really fundamental to humans, right? Moving people or flying, moving people around, building trains, building siege engines. All of those things run up against some sort of an energy conservation law. Nature makes it hard, or mathematics make it hard. But it's something that you need to do anyway. Stuff needs to get moved around, fortresses need to be defended and taken, and so on and so forth. So, and again, this is my disclaimer to any fellow academics in the room. I'm not going to talk about the hacker community and define the colors of hats. I'm going to talk about, look, this is a community that communicates, reproduces itself by communication. New generations come in, learn the skills, and affect the actual industrial real-world state of the art. So no matter how you think about it, it's a reliable transmission of skill, intuition, and method. And with something that produces so many results and shakes up the state of the art so much, there has to be a methodology to it, whether people call it that or not. So, the major human need. Humans cannot function without trust. Trust is something that makes, in my personal experience, the difference between a completely miserable existence, economy, culture, and a much more acceptable one. So we need to trust something or someone every day. I am going to refer to a higher authority. on human condition. Those crimes, those bad things that land you in hell, right? They are ranked. The deeper you go, the more serious you are. And guess what the worse your effect on the overall human condition is? Where did Dante put betrayers of trust? The 9th last circle of hell. So it shows just how, and certainly in those times, life was a lot less ordered and trust was a lot less important. So we're talking about something that is absolutely crucially human. This is the need that you can't forego. This is the need that hacking, in fact, addresses as a separate, distinct discipline or human pursuit. And it addresses it in software, hardware, and human-in-the-loop processes. So it's something that has to do with computers, but again, I would refer to a higher authority. Who cares about what a particular academic says? How about trying to persuade a hacker to define the essence of InfoSec? And here is a quote from FX and Bratsky's talk at a scientific conference. And I quote, "Pragmatically, InfoSec is about working towards computer systems we can finally trust." Also, see Andreas's talk, Defense is Not Dead. It happened yesterday. You'll catch it on video, I think. So hopefully I've convinced you that trust plays a major role in what we do. Now, let's just take an aside and ask ourselves, if manipulating trust, if testing trust assumptions is so important, how many schools actually teach a class in social engineering? You can't pen test an organization. You can't do a security assessment without it. It won't be complete. How many schools actually teach it? I'm aware of just one such course taught at the UIT by Shelley Keating, who might be in the room. If not, I'll tell you how to get in touch with her later. But this is basically the only course that I'm aware of that tries to define techniques of manipulation of trust, literature review, ethics, and so on and so forth. Just what does that tell us about, how academia relates with real world and needs of real world? Interesting. Let's get more technical. What does trust in computers mean? One of the many sociological definitions of trust, operative definitions of trust, is that the trustee behaves as expected, despite potential capability to violate expectation. So what does that mean for code? The code does what you expect it to do. A router does what you expect it to do. It behaves as expected. Only expected kinds of computations occur. Again, on an entirely personal note, a server dropping a shell represents a computation that should not occur, right? There is no code for that. All the nice abstractions do not allow for that to happen. Like my syslog dropped a shell, and I was like, uh-oh. And that was one of the defining moments of my existence. So, brought to you, look, I've been taught about Turing machines and finite automata and all of those things, and I know the Chomsky hierarchy of computational powers. And how come this computation happened that caused my syslog to drop a shell? Interesting. So the rest of this talk is brought to you by the letter C, complexity, composition, and computation, quite conveniently the 3 C's, all core subjects of academic CS. Composition. The way systems are built in real world is they are composed out of pre-existing pieces. No one writes anything much from scratch anymore. Composition of computational systems has very bad mathematical properties. When you figure what computation a composed system is capable of, it very quickly gets undecidable. as in the halting problem kind of undecidable, meaning it will be very, very hard to write a tool that does anything meaningful unless you find a really nice special case by intuition, basically, and a lot of heuristics. So that makes it really, really hard. This is the mathematical challenge. People express it in many different ways. Joshua Wright says that despite any sort of theoretical protocol analysis, security does not get better until hacker tools establish a practical attack surface. So you pound on it. You study it from many, many different angles, because that's the only way you can approach an undecidable problem. Now, you go to a CS school, and you learn about finite automata, irregular expressions, and push-down automata that give you recursion, and then Turing machines that give you everything. So computer science is really concerned about what computations are possible, what computational platforms can perform which kind of computation, and so on and so forth. So it's the negative results are really a core subject. So you've got finite automata, you've got push-down automata, you've got endless tape Turing machines, and then you've got reality. So engineering is about composition. Systems are composed, and composition has this way of producing really interesting results. Quoting another, so composition kills, you may have heard this as complexity kills. Well, again, complexity is what arises out of composition. So what happened in practice is, despite the best of intentions of theoretical computer science, to deal with different kinds of computations and define what is possible, what is not. This is the fundamental question of a computer science. Here, have this machine, what can you compute with it? Despite all this, real systems, due to composition, got too complex for theoretical analysis, for meaningful theoretical analysis, really, really fast. And the typical situation is that actual systems are more computationally powerful than intended or expected. And this tells the story of every exploit. An exploit is a computation that, well, the original machine has not been, should not have been able to perform. So theory moved to theoretically tractable issues, models, prototypes, proofs, and there is a very good organizational reason for it. Intractable systems are extremely hard to publish about and to show novelty in your publication, and to pass peer review. And we've been dealing with some of the interesting effects of this in the most recent automatic exploit generation controversy. CMU group, Brumley and others, published a paper that proposed a system that fundamentally changed the world, making automatic exploit generation within reach of the least qualified attackers, and at least such was the claim. Look it up. It's a really fascinating discussion as to why academia behaves the way it behaves. So, the need to trust computer systems, the need to predict the computational behavior, has been with us all along. It's a part of the human condition. So, I posit that what happened is, with this need being there and being felt by everyone, although maybe not put in so many words, the hacker community stepped up to fill it. And this is what it has shaped up to be. It's a practical trust analysis of actual behaviors, of actual computer systems. So, if we try to define the methodology of how things have been proceeding and how those state-of-the-art contributions and revelations as to what is computable and what's not have been achieved, you see several important prominent features. First of all, while engineers go layer by layer and so abstract complexity and so achieve their composition, your typical exploit is usually cross-layer. People refer to it as abstraction leaks, leaky abstractions. People refer to it in many different ways. I prefer to say that boundaries of layers become boundaries of competences. What that creates is inside your actual machine, you find weird machines that you can program. They have unintended automata or Turing machines right inside of them, and they are programmed by crafted input. So engineers go by layers. And as we all know, layers are magical. And it's enough to secure just one layer for the whole system to become trustworthy. Not quite. So here is the best piece of OS course, operating systems course reading that I ever found. It's a FRAC 59.5, Palmer's of Tim Tesso. The story of going in depth in constructing a rootkit through all of those layers, practicing the deceptions that are inherent to each one of those layers, and in the end, emerging to the dynamic linker through the very guts of the kernel that does the file system drivers and the loading and the creation of virtual memory spaces. Main design principle of rootkit engineering. Now, where exactly can you find information of this in non-hacker space? There are millions of books, probably, that teach you something in 21 days and unleash the dummy in you or something like that. There is only one accessible book by John Levin called Linkers and Loaders. Linkers and loaders are things that actually do composition and put things together. It happens every time. And in order to understand how binary formats works, how linkers work, how loaders work, you have to go read Silvio Cesare or the wonderful offerings of the Aresi team, or the GrugQ on the dynamic linker in particular, or Uninformed, that is just about the most lucid piece on how relocation works and how you can actually use the automaton that does relocation to obfuscate and deobfuscate code. So you find those weird machines, those weird environments which you can program as results of composition. And usually it's something like a memory corruption that you can use to reliably overwrite a place in memory. Well, that's your move, that's your weird move. Or you get your weird branch, or what have you. These are also known to people who do SMT and theorem proving as reliable implicit data and control flows. So instead of talking about automatically generating exploits, maybe we should be talking about automatically deriving minimal descriptions of those execution environments. What gives you that weird machine? Well, these are, of course, gadgets for return-oriented programming. So let's look at the return-oriented programming timeline. The original idea, 1997. 1998, an elaboration by Rafal Wojciech on the original Solar Designer post. Tim Newsham explains how to do frame chaining. Now, it starts looking like programming. It starts looking like chaining together so many tickle or forth calls. Nergal in FRAC, around 2000, 2001. Tyler Durden, they describe the technique in great detail. Now, you can actually program it and people start doing it. Well, 6, 7 years pass. Academia becomes alerted to the fact by Hovav Shacham, who calls this practice return-oriented programming and proves that it is Turing complete, at which point, the first point in 10 years that academia sits up and takes notice. And then, of course, more hacker research follows. So this is, again, my favorite, one of my favorite FRAC articles, bypassing PAX, by way of co-opting the dynamic linker as an elementary operation of the exploit. ASLR, sure, but the machine already has the component that does ASLR. That does resolution of symbols. It's a dynamic linker. Let's return to it and have it actually load the library. It's a part of this machine. Oh, but what's that? BugTrack 2000, Hera publishes this. Let's read this. I present a way to code any program or almost any program in such a way that it can be fetched into a buffer overflow in the platform where the stack another place in the memory, but libc is non-executable. Really? So this is the first idea of return-oriented programming being something of a return-oriented program, being something that you can compile. This is 2000. This is BugTrack. This is one of my sites at the beginning of the talk. And of course, now we have fully functional compilers. It has gone way beyond the idea. Notice the spread between exploitation in practice, as discovered by the hacker community, versus when the problem got noticed and got analyzed by academics. Haroon Meir, History of Memory Corruptions in Black Hat, is a wonderful, wonderful history of things that have been used as elementary instructions for programs. Should be. History of memory corruption-based programming, perhaps. Creating extra computational power since since whenever. Another revelation that I had at PH Neutral was Len Sassaman's and Meredith Patterson's talk, which they repeated at Black Hat, at which point it was recorded. I really, really urge you to look at it. Has the key insight. You can take this thing about composition and computation and how composition creates undecidable problems much, much further. You can actually make it formal. The key insight from their SSL exploitation, which produced a whole bunch of exploitable bugs for a good reason, is that security of the SSL CA client interaction is formally predicated on computations performed by the parser on both of those points being the same. We're talking about something that computer science proves, at least in theory. It's computational equivalence. Yet, verifying that two parsers of the power that you need to parse SSL is undecidable. These languages are require too much computational power. Let's take it a little bit up one notch theoretically. So here is how composition and computational equivalence result in undecidability. Undecidability means that you cannot hope to write a tool, a program, that will solve this problem in general. What this intuitively means is that unless you're lucky and there is a good partial case or a bunch of good partial cases, you are basically not going to get much improvement no matter how much labor, no matter how much capital you throw at the problem. Undecidable problems are very, very hard to solve. You don't make incremental progress. You don't make incremental progress by just applying more labor. I stand corrected by someone in the audience. If the protocol requires more than a non-deterministic push-down automaton, which is to say it needs to, whatever your protocol is, the language of your protocol, is deterministic context-free language, verifying equivalence of those two pieces, or what those two pieces would do on the same piece of data, such as a common name in assigning request versus assigned certificate, is undecidable. And guess what? Normal recursive structures like balanced parentheses, palindromes of open close, are actually not a deterministic context-free language. So, other non-equivalence examples. Once I got the idea, I realized that it was actually throughout the hacking experience. One of the best papers on IDS evasion, Ptacek, Newsham, all sorts of fragmentation tricks, they're all predicated on the protocol parser and the stream reassembler being producing the same result, being computationally equivalent for some model. to the reassembler or parser on the target. You can make your, if you can make your IDS see something that the target is not seeing and vice versa, the IDS is useless. The usefulness of the IDS is predicated on the IDS seeing the same picture, doing the same reassembly. Fingerprinting. You throw stuff you throw inputs at the machine, and you can tell that this is a machine that's this vulnerability. Well, it's different computations on different architectures, computational non-equivalence. Hypervisor red pills. Again, computational non-equivalence left as exercise for the reader. Good luck proving computational equivalence of something that is a machine that runs another machine, that is actually a Turing machine. So we sort of build those little computational systems, and suddenly they just grow and look at us from up there. You're like, want to trust me? Oh my God, it's Turing complete. Anyhow, the Martian, I think that was supposed to be a Martian tripod. Data flow and security. Really, really interesting topic, which again goes back to computation as the fundamental object of computer science. Memory corruptions, in-band signaling, create implicit data flows. The essence of exploitation has been, for a grand many areas and techniques, turning those implicit data flows into control flows. DJ Bernstein, in his wonderful paper on the 10 years of QMail security, which you will agree has quite an impressive record of security, wrote that suppressing implicit data flows is a lot more useful than the holy grail of what was believed to be the basis for engineering securing systems, the least privilege principle. In fact, he called the least privilege principle a distraction in his attempts to create a more secure piece of software. So instead, it was about implicit data flows. Now, those implicit data flows is exactly what happens across layers, create Turing-complete environments, and those weird machines, what have you, however would you like to call them. It is what runs the exploit. So there are two approaches here. You can prove the absence of those data flows. No, hello, SMT solvers and provers, and all of the great formal apparatus that you start seeing being presented at Recon, at DEF CON, at Black Hat, and here. And this is, to me, a great development, because I can't really, I really don't know about these things, not as much. And whatever I learned, I just happened to learn better from the hacker sources, and so perhaps they will teach me. What you can also do, if you give up on the dream, or if you do not quite buy the dream of writing flawless software with, say, a language that allows you to do so more easily, is to block those data flows and thwart the creation of your weird machines and execution environments when those occur. And there was actually a whole area of engineering, of computer engineering, called tagged architectures, that allowed you to tag memory and trap those data flows when they were out of line. And this is the old Orange Book, US Department of Defense. And since I'm colorblind, I have to sort of believe that this is orange. It could be something else. But the idea is that each principle, say a process, is labeled. All data are labeled. All data is labeled. And those labeled are continually being checked on all operations by a reference monitor, which is the most trusted part of the OS. And you've got a few formalisms, which I think most people know. They come down to those labels forming a lattice with natural operations like find me a parent or find me a common child. Because sometimes you need to create a label for someone who administers the context. And sometimes you need to create a label for someone who shares the context. Now, there was actually hardware like that. And it just died. And we ended up with x86 that supported no labeling at all. 2 minutes. That supported no labeling at all. You could not tell data that sort of like sits there from the code that sort of like does things. Of course, since you've got all sorts of interesting data flows that you can turn into control flows, that doesn't completely cure it, but hey, let's make a start, right? In fact, a wonderful thing happened. Pax and OpenWall, hacker projects, brought tagging back on x86 for the purpose of emulating the non-executable bit, which was a legacy of Multics and other better designed operating systems. Sort of. The tags were page granular. And they were spread across bits in x86 segment registers and and page table entries. And it's like you look at this x86 memory translation, and oh my god, the split TLB allows you to stick a part of the label, which is semantically that this is something that does stuff, code, versus this is something that gets stuff done to data. And you find part of the label in the code segment descriptor, others in the data segment descriptor, and this works because there are two hardware paths along which data and code are fetched. And oh, by the way, another part of the label sticks in the page table entry. This was the resurrection of the old tagged architecture idea to me. And it's like Christmas. It's like, well, NX, no, okay. Labels really close to the objects they are supposed to protect, and enforcement being done by trapping, which is the most efficient way to do that. And the page fold handler became hugely overloaded as a reference monitor. And, well, I need to end abruptly, but I'm pretty much done. So this would not, I don't know how illuminating this was to you. It's very hard to share something that seemed like a revelation at the time, and I'm still under the impression of that revelation. And I will stand by my statement that I learned a lot more about the fundamental objects of CS from hackers, from hacker publications, other than from CS courses. And I need to thank a huge number of people, Recurity team and FX, for listening to this rant first, and and encouraging me to give it. Lance Asselman and Meredith Patterson, who showed that perfect example of how composition provides an undecidable problem of computation, or verifying a computation. Shelley Keating, who teaches a course in social engineering alone. Erin there for folks for many discussions of practical issues, and many, many others. And again, thank you.